Thanks for inviting me, Daniel. I'm just going to tell a story, sort of, in numbers, but Daniel, it's not as exciting as the Pink Floyd story, but it's pretty exciting. So, when I was a freshman in college, for the first time I got interested in numbers. And I got interested in patterns and abstractions and theorems and proofs, and I didn't know much mathematics because I just had one semester of calculus. And so, I played around a lot with patterns. I was interested, and one of the things I was really interested in was prime numbers. And so you may have heard of the function pi of x. It has nothing to do with the number pi, but it's the name of a function, pi of x. It's the number of primes less than or equal to x. And I was fascinated because I read that there was no known closed form formula that had been discovered for this. I'm like, yeah, maybe I can do this. All right? So, and I'm going into this problem really naive, right? No classes in number theory or anything. Just remember the word naive, okay, as we go along. I think I did know about the Sieve of Eratosthenes from about the 3rd century BC. If I didn't, it doesn't really matter because this is kind of the most simple algorithmic way to generate the prime numbers. So let me show you what I mean. You just write down the natural numbers and you say, okay, the first prime number is 2. Don't ask why 1 is not a prime number. If we have time later, you can ask that. But 2 is the first prime number, and then you want to get rid of all the composite numbers, so you just strike off all the multiples of 2 except itself, like that. And then that means 3 has to be the next prime number, so you strike out all the multiples of 3. Now that's going to be a 6, so I'm going to strike it out twice, and 9, and 12, and 15, 30. Let's see, 2, 3, 4, not a multiple of 3. 2, 3, a multiple of 3. Okay? And then 5 has to be the next prime then, and I won't bore you with this too long, but let's see, 10, 15, 30 would be in there, and this one would not, and this one would. Okay, so I became very interested in some patterns I saw in the Sieve of Eratosthenes. You see the idea, you just sieve out or you strain out the primes and you let the composites go. Okay, so I became very interested in this composite because it's 2 times 3, and I began to get very interested in this composite, 30, because it's 2 times 3 times 5, right? And I was also really interested in 2 times 3 times 5 times 7. So I was interested in numbers of the form P1 times P2 times up to PQ, the product of the first Q primes. I found some interesting patterns with those numbers. So 6, 30, 210, and so on. What I wanted to know was, I wanted to know how many numbers less than this are not divisible by these primes. So I wanted to know the number less than or equal to this product that are not divisible by P1, P2, up to or PQ. Okay, so it's not divisible by the first Q primes. That's kind of like counting prime numbers, So I thought, hey, I'd like to understand this. So let's just look for a pattern, all right? So I said, all right, I'm going to look at 2 times 3. And I want to know the number of numbers less than or equal to 2 times 3 that are not divisible by 2 or 3. And you say, well, you can just count them. Right, but I want to look for patterns, right? So how many numbers are less than 6? Well, less than or equal to 6. Well, there's 6. And then I have to subtract out all the multiples of 2. So I'd have to take out half of those. And then I have to take out all the multiples of 3. but I've double counted. I took something out twice. The number 6 was taken out each time, so I have to add that back in, okay? And so I'm going to write it like this. Instead of saying +1, I'm going to write it as 6 over 2 times 3. That's a special way to write +1, right? Yeah, so interestingly enough, when you factor out the 6, you get a neat looking little kind of a series. You get 1 minus a half minus a third plus 1/6. Okay, and that turns out to factor very nicely. And I'm like, yeah. And then 6 is 2 times 3. You can put the 2 here and the 3 here, and you get 2 minus 1 times 3 minus 1. Okay. Oh, wow. The number of numbers, not primes, but the number of numbers less than or equal to 6 that are not divisible by 2 or 3 is 2 minus 1 times 3 minus 1. I want to do one more with you, and then we'll move on. Okay, so what about the number less than or equal to 2 times 3 times 5 that is not divisible by 2 or 3 or 5. Okay? I'm going to use the same counting procedure. So there are 2 times 3 times 5 is 30. There are 30 numbers less than or equal to 30. I got to take out all the multiples of 2. So that's half of them, right? I have to take out 30 over 2. I have to take out the multiples of 3. I have to take out the multiples of 5. Okay? Now, I've double counted some things, right? So I have to add back in the things I took out too many of. So I got to put back in, and this is going to go a little bit more quickly than what I did it the first time. But so I got to add in the multiples of 6, the multiples of 10. What do you think the next set of multiples is that I have to add in? 15, right? So 3 times 5. And it turns out, what about the number 30 itself? Okay, because it's not divisible by the first 3 primes, right? So here I took it out, here I put it back in, and so now I need to take it out. So 30 over 2 times 3 times 5. Now, you can factor out a 30, and you're left with this neat series of numbers, and it factors, yes, and I bet you know what it factors as. Now, 30 is 2 times 3 times 5. I'll put the 2 here, the 3 here, and the 5 here. Does anybody see a conjecture in the air? Yeah, and I'm like, whoa, I can almost feel my heart pounding like it did, you know, when I figured that out. And it took more than 5 minutes. But I was able to prove, you guys, that the number of numbers less than or equal to the product of the first q primes that are not divisible by the first q primes is actually equal to the product, and this is the product sign. It's like a sigma for adding. The product of pi minus 1 as I goes 1 to q. Like, whoa. I thought I was, I felt like I was peering into the depths of the universe. I'm like, this is really cool. All right, so this was my first theorem in this particular project. All right, let's remember that. Then I said to myself, this is almost like counting primes. Man, I'm getting close. And so I said, the thing is, you got a couple problems. One problem is trivial. Like if I'm looking at 6 and I count these things, well, it's not going to count the primes 2 or 3 because they're divisible by themselves, right? So I have to throw in the first q primes into my sum if I want to get the number of primes. And then 1's always kind of a pain in the neck. you have to take that out if you're looking for prime numbers. Anyway, that kind of falls apart up here because look here. What is the prime factorization of 121? 11 squared. Look here. If I look for the numbers less than 210, less than or equal to 210 that are not divisible by any of the first 4 primes, I'm going to pick up 121, and that ain't prime. That's composite. And as you go further and further out the number line, this function that I came up with is counting more and more composites. We don't want that. So we say, all right, so what is the smallest composite number that cannot be divided by the first q primes? So like let's think about, which one would be the best to look at. So let's look at 6 here. What is the smallest composite number that cannot be divided by 2 or 3? What is the smallest such composite? Well, every number can be broken into prime factors, right? So it has to have a factor of 5 if it's not divisible by 2 or 3. But 5 is prime, and so the next smallest composite would be 25. It would be 5 squared. And so my second theorem that I proved, and let me write this down, was very good. So the second theorem that I proved was that the smallest composite not divisible by P1, P2, or PQ is, you tell me, what is it? PQ plus 1 squared. Beautiful. See, if you'd been doing this, it would have taken you less time than it took me. Okay? Now, but I want, so see, as this product of primes scoots this way, this begins to lag. The PQ plus 1 squared begins to lag behind. And yet I wanted to get as close to this PQ plus 1 squared as I could so that everything behind that would work for my purposes of estimating this. Okay, so what I wanted to do was I wanted to take x to be between PQ plus 1 squared and PQ squared. And we're almost done here. I wanted to take x to be between those two squares of adjacent primes because this makes it big enough for my purposes, but it's small enough so that anything below x that's not divisible by the first q primes is going to be prime or 1. Cool. So I said to myself, let's draw a picture. There were actually many pictures, but I said, all right, here's the interval from 1 to the product of the first q primes. Okay? And then I get this other interval that tends to lag behind a bit. My x. And, you know, like a little further on somewhere is PQ plus 1 squared. So I get x up there. And I know how many numbers are in this interval. I know exactly how many that are not divisible by the first q primes. That was theorem 1. That's exactly the number in this interval that are not divisible by the first q primes. I also know exactly how many are here and here. Okay? It's the number of primes in this interval. But then remember, we threw out the primes themselves in our counting procedure because they are divisible by themselves. So I have to add in what? How many things do I have to add in? Have to add in, no, actually I have to subtract them off because pi of x counts all the primes, where my procedure is not. So I actually have to take q, the first q primes off, and then I have to add 1 to include the unit. And this number is exactly the number of numbers on this interval that are not divisible by the first q primes. And look at that. Look at that. So I said to myself, I said, okay, so what if I write this? Product I goes 1 to q of the pi minus 1. That number, that quantity, is to the product of the first q primes as, sort of, as, what would you write next? What would you write in the numerator here? You got it. Pi x minus q plus 1 over what? Right? And so therefore, and man, I'm getting excited now, see? And therefore I said, hey, pi x must be approximately equal to the number x times the quotient of the pi minus, product to the pi minus 1s divided by the product of the pi's. And then you have to add q to add in the first q primes, and you have to subtract 1 to get rid of the unit, because it's not considered prime. And so this was my big idea. Okay, well, any of you could have done this. I spent a lot of time playing with numbers, patterns. I didn't have to know anything except what a prime number was. And boy, when back then I couldn't just get on the computer and generate these things, so I had to find a table in a book that gave me values of pi of x that people had computed forward. And there they are in the second column. And then I computed my approximation, which is in the next to last column. And then the very last column is how far my approximation was off. And you can see, man, was I ever excited. Because the other approximations, like x over log x, get pretty far off fast. Well, without going into much detail, let me just tell you that I wrote this up and sent it to the Journal of Number Theory. And in due time, which is usually a long time, in due time I got a referee report back. Now, referees are the people, the experts that the editor sends the paper out to, and then they send back their expert opinion, and the editor decides whether to accept the paper or not for the journal, and then tells the author. This paper has been rejected from the Journal of Number Theory. And then I got this really nice letter from the referee. He says, or she, I don't know. Back then there weren't too many women mathematicians, but there are now. But anyway, he or she says, this is really neat. Very nice letter. Theorem 1, which I've erased, is a special case of Euler's totient function theorem. Very nice. This was done in the 18th century AD. And this counting method, it's called the inclusion-exclusion method. And that was done by Legendre in the 19th century. And so, I know this is kind of silly. It sounds silly, okay? But think in your own heart. I had sort of wondered if I might be Einstein too or something, And suddenly, I felt like an ignorant imposter. And when you study mathematics, you tend to oscillate between these two poles. And the more you learn, the less oscillation there is, right? And then for most of us, we don't turn out to be at either extreme. But what I want you to get from this talk is the phrase naive exploration of patterns. And I forgot to tell you that when I wrote up my paper and submitted it to the Journal of Number Theory, it said on the front, it said, Shandelle Marie Henson, sophomore, Southern College of Seventh-day Adventists, right? No wonder the referee was so nice to me. Oh, this is a sophomore. Okay, she doesn't know what she's talking about yet. This is naive exploration of patterns. That is one of the quickest ways not only to become a mathematician, but to, I think, hone your analytical skills. Looking for patterns, playing with numbers and abstract objects, and just looking for patterns. And do it when you're still naive about all the theory, because once you learn the theory, you won't be nearly as creative. But if you do this before you learn the huge structure of theory that already exists, you will reinvent many, many wheels. And every time you reinvent a wheel, your mathematical growth is going to surge forward. Okay, so you may feel like an imposter, but look, if you're thinking up the same thoughts that Euler thought of and Legendre, and how can you go wrong, right? And then after you get all the theory and the training, you'll be able to go a little further and actually do something brand new. But here is a real exciting thing, is naive exploration. I love to be a novice. You can make so much progress when you're a novice. I love it. It's fun. It is just so incredibly fun. I had the opportunity to share this with Andrew Wiles at Princeton. He's the one that eventually proved Fermat's theorem. And I had the opportunity to sit down with Andy Gleason at Harvard and talk about this. And we just had a blast. And I didn't go to grad school at either of those places, but what fun. And so I hope you will have fun too in your naive explorations.